Today's topic is box kite analysis by Clouds. The box kite is made out of a frame, crossed braces for support, and two sections of lightweight fabric or material separated by empty space. The box kite was first developed by Lawrence Hargrave in the late 1800s. He used a train of box kites to lift himself off the ground in 1894, an aeronautical feat at the time. Alberto Santos Dumont used the box kite idea to build and fly the 14 bis. It was the first flight of a heavier-than-air machine in Europe. For this project, the difference in the lift generated from the box kite at a 0-degree angle of attack was compared to a 60-degree angle of attack. Additionally, the number of standard box kites needed to lift a human, much like Lawrence Hargrave, was explored. Fluent was used to analyze the kite. First, the geometry was generated in SolidWorks, and then an ANSYS enclosure was made around the kite. Next, a boolean was created to subtract the kite geometry from the enclosure. The space surrounding the kite was then meshed. In Fluent, the steady, pressure-based solver was used because the 10 meter per second wind velocity used for the analysis is slow enough to warrant an incompressible solver. The K-epsilon turbulence model was used because it is a good model for flow over complex geometries that have normal pressure gradients. The consistent, simple solution method was used for the analysis. Additionally, for the solution methods, the second-order upwind was used for all variables, making the solution second-order accurate for pressure, momentum, and energy. The solution converged after 500 steps, which shows that the solver was stable. The initial velocity was set to 10 meters per second and either entered at the angle shown for the 60-degree angle of attack, or, for the 0-degree angle of attack, the flow entered perpendicular to the y-axis. For the boundary conditions, the positive y and z axis were set as velocity inlets and the negative y and z axis were set as outflows. The analysis was run for 500 iterations. These photos show the velocity of the flow over the kite on an isosurface located on the XY plane. For the 0-degree angle of attack, the greatest velocity was experienced at the braces located on the box kite. Flow decreased over the braces in the 60-degree simulation. Lift and drag coefficient data was collected during the analysis on every section of the box kite. For the 0 angle of attack, the magnitude of the lift coefficient was greatest on the first side that encounters the wind and it equaled 0.29. The lift coefficient on the back side was 0.05. As expected, the lift generated on the top wing was equal and opposite to the lift generated by the bottom wing for the front and back of the kite, so the net lift generation is 0. For the 60-degree angle of attack, the lift coefficient was only positive on the positive z size of the kite. The remaining lift generated was in the negative direction. Nonetheless, the net lift generation is 7.23, a surprisingly large lift coefficient for the box kite at a 60-degree angle of attack. With the lift coefficient results from the simulation, it was found that net lift for the box kite at a 60-degree angle of attack and 10 meter per second wind is 411.4 newtons. The average North American adult weighs 80 kilograms, or about 177 pounds, which equates to 784 newtons. Therefore, it would take about 2 box kites in 10 meter per second wind to lift an adult, similarly to Lawrence Hargrave. 2 kites at a 60-degree angle of attack would lift an adult, but once the desired altitude was reached, a 0-degree angle of attack would be better suited for maintaining altitude. The box kite aided in the advancement of aeronautics in the 19th century. Today, it is a great way to spend a beautiful spring day.